moistures of the solid is the moisture of the product initially minus with the moisture of the mass of moisture, sorry. The mass of solid is equal to mass initial minus the mass of moisture, which means that the moisture that inside your food lah. Okay. So how to calculate the mass of moisture is the initial mass of your food multiplied with the moisture content weight basis. So this one is you obtain from the moisture analyzer. So for example that if you if you know that is 80%, so multiply with the mass of the product, you can actually know the mass of solid. So I repeat again, so to calculate the mass of solid is equal to the mass of product minus the mass of your moisture. So how to know the mass of your moisture is the mass of your product multiplied with the moisture content weight basis. So this one you obtain from the moisture analyzer. So then you will actually got the moisture, the mass of the dry solid. Okay, and then in step 2, you need to calculate the moisture content of dry basis for each time, okay, each time interval. So that's why this is actually the formula lah, which means that the MP is the mass of the product at every time interval divided with the mass of solid. You divide with the mass solid, you will get the moisture content dry basis. So remember, this one is actually the moisture removed at that time divided with the mass solid. That's why it is dry basis. Okay? Like I mentioned last week, when talking about drying, usually we actually use the dry basis. So that's why here is actually the moisture content, mass of moisture divided with the mass of solid. So to calculate the mass of the moisture is you have to use the mass of the product for each time minus the moisture of solid. So that's how you actually can get the moisture content of dry basis. But this one we will see the example later in the Excel in our activity, so that you can actually understand more how to actually get the moisture content of dry basis for each time lah. Okay. So this is the graph of drying curve. Okay, you can see that the percentage of moisture with the y-axis is actually the time. Okay, so this one shows you what happened to the moisture when we do the drying process lah. So you can see that in the beginning of the drying, we also call it as an initial stage. Okay, this one we call it as a settling down period. So in this initial stage, what happened is actually this one is actually when sensible heat happen. Okay, which means that remember we have sensible heat and also latent heat. Sensible heat is actually when the temperature change happen. So that's why here this one is the when the temperature change happen lah. So which means that we add heat to the system. So that's why in the beginning we cannot actually see the rapid of the removal, but we can see the initial time where it's the moisture is actually it's not that constant. It's actually it's in a small amount of water removal, and then when it starts to reach at certain point, so to know this one is actually start the constant rate period. So to know the constant rate period is actually when the time is become constant lah. Okay, so we can see that at this time the rate of removal of the water is actually the same. Okay, and then this one is actually the time where the moisture diffuse from your food to the surface. Okay, and this one is actually where the combination of the convection and also the conduction happen lah. So which means that convection, remember the keyword is the solid and the fluid and solid, and the conduction is solid lah. Okay, so here after certain times, okay, when all the moisture diffuse to the surface is actually remove the water to the air. Okay, it started to become falling rate, which means that the removal start to become gradual. It's not rapid at all. Okay, so it started to remove little by little. It's not that high compared to the constant rate, and the point where it change from constant rate to falling rate, we call it as a critical moisture content. Okay, the moment where the constant rate change to falling rate, we call it as a critical moisture content. And then it will remove the remaining of the water from the surface, which from the evaporation process. So it will reach the equilibrium moisture content. So at this equilibrium moisture content, you can see that there's no more moisture being removed from the system. So this one we call it as the moisture equilibrium moisture content. So I repeat again how to actually interpret this drying curve. So what happened during the drying process is happened first, which we call as the initial stage of the drying process. So you can see that this one is actually when the sensible heat happens. So we adding the heat in the system and the temperature change. So which means that the from low temperature it become high temperature. So if the removal is not that high, but then it goes for the constant rate period. So which means that the removal is actually constant, and this is the period where your moisture diffuse to the surface, and the moisture also, the vapor of the moisture also evaporated to the air lah. Okay, and then at certain point it will reach to the falling rate period, which means that it does not constant anymore, it become falling. And at this falling rate period, the moisture content removal is not that high, but then this one is actually the moment where the most of the moisture from your food already been diffused to the surface, and this is the point where the water from the surface is evaporated to the environment. And the point where the constant rate change to the falling rate, we call it as a critical moisture content. The constant rate change to the falling rate, we call it as a critical moisture content. And then it will remove the water until it reaches the equilibrium moisture content. And this equilibrium moisture content is actually the moment where there's no more moisture being removed from the system. And at this point, usually the moisture content of there's no water being removed, and the water activity is actually equilibrium to the relative humidity of the environment. So that is actually the point where it reached the equilibrium moisture content. So any question related to the drying curve before we go to the drying rate curve? Okay, no question. So now is this one is actually the drying curve when you plot a wet basis moisture. Remember that when talking about moisture content, when we report it in the wet basis, it's actually the total, the moisture removal divided with the total. That's why here the percentage is 100%. Okay, so which means that from the beginning is 90%, 85% for example, and then it goes for the at the at like around like 5%. Okay, so this one is the moisture the drying curve if you use wet basis moisture content to plot here. This one is a wet basis, but then if you plot it in the dry basis, it will become like this one lah. Okay, dry basis. We do not use a percentage, we use a gram per dry product, which means that this is the dry basis. So this is how your moisture be removed from the system. So you can see that initial, the constant, the point where it become changed from the constant to falling, and when it's actually the time that it become zero. So it's actually the point where the equilibrium reach lah. Okay, so this one is the water removal rate. Sorry. In the beginning, we have covered the drying curve. Okay, so which means that water removal, moisture content versus time. So now we're going to plot another graph. We call it as a drying rate curve. Okay, so drying rate curve is actually from the name itself, you know that the moisture rate, the water removal rate, to plot the moisture removal rate lah. Okay, so how to actually get the value of moisture removal rate, or we call as the water removal rate, is here is the formula. So you can see that weight of water removed in the interval per time divided with the mass of solid. Okay, so you can see here is actually the water removal over the dry solid. Okay, which means that the moisture content of dry basis, okay, divided with the time. Okay, so you can see here the moisture content removed divided with the moisture of solid is actually the moisture content dry basis. Okay, this one is the time interval, so divided with time. So basically, when talking about the water removal rate, you wanna know, you wanna use the moisture content dry basis over time. So you can see here the moisture content of water removed divided with the moisture, the mass of solid is actually the moisture content dry basis divided with time. So we're gonna see in the Excel after this. Okay, so basically this is actually the example where you can see that this is the water removal divided with the amount of solid in that product, multiplied with the time. So you will get the water removal rate around 0.0209. Okay, water removal rate is water removed divided with the solid, the mass of solid multiplied with the time. So 22 gram of water being removed from the system, and that product is actually around 70.2 gram of solid, and the time required to remove 22 gram is 50 minutes. So that's how you get the amount of 0.0209 gram water per gram solid per minute. So this one is also trying to explain to you about the behavior of the drying lah. So before this, we only plot the drying curve. So this one is actually the water removal rate, or the we call it as drying rate curve. Okay. So what happened is you have to plot like this one, which is the removal rate over time. But also this one, you also can see the initial rate here, the constant rate, the falling rate, and here is actually the critical moisture content where the constant rate changed to the falling rate, and this is actually the equilibrium. Okay, equilibrium time lah. And also this one also trying to explain to you about the behavior of the removal of water, but this one is actually the graph of drying rate with the moisture content. Okay, so which means that here is the initial, the constant rate, the critical moisture content, falling rate, and falling rate lah. Okay, you can see that the behavior, what happened during the drying lah. So which means that to actually identify the falling rate, constant rate, the critical moisture content, the equilibrium, you actually can plot like the moisture content versus time, the drying rate versus time, and also the drying rate versus moisture content. So you be able to identify when is actually the time it become constant, it become falling, and you can actually know the critical moisture content and also equilibrium moisture content. Okay, so this one has been explained to you. This one you can actually read if you want to understand about the initial, constant, and falling. But this one has been explained to you guys lah in the beginning of the class. Okay, so this one is the psychometric chart. Remember that this one is actually about the environment. So we have learned in these 3 weeks, it's actually about the drying and what happened to the product, and the drying and then the psychometric is actually about the air lah, which means that you have understand about the environment before this in the food engineering class. Okay, so this one is just the explanation what happened to the constant rate and also falling rate for the graph that we have. I have shown you guys just now. Okay, so this one also about the graph, the same thing, and also the explanation is actually the same. Okay, so now we're gonna do class activity 2. So I want you to open your Excel lah. And this one I have uploaded in the Putra Blast, so you can actually open the Excel. So do not worry if you get left out in the maybe you cannot change the speed of my teaching for this class, because like in your graph, okay, in your Excel, I have put the what do you call it? I have put the not just the empty Excel, but also have uploaded the answer lah. So if you can, if you do not catch up my demonstration, you can actually go step by step lah. Okay, like this one we have like step 1, okay, step 1, step 2, step 3, step 4. Okay, 5 here we have the, it's actually 5. Step 5, I can't remember. But then we have step 5, step 6, 7. Okay, so I'm gonna demo to you guys. Okay, the how to actually plot the drying curve and the curve rate. I think this one for those have done the result part for the drying, you have tried to use this one, but I also have put the empty Excel and also the answer lah, so you don't have to worry. You can actually try this at home, but try to do it and try to submit the class activity in your Virtual Blast lah, because that we have today the class activity drawing curve and also the assignment lah. So for the drawing curve, you just have to screenshot no easy, you just have to screenshot your Excel, or maybe easier just submit your Excel that you'd have to try lah. So you can actually submit your today's class activity to the class activity to here. Okay, you whether you want to submit your Excel file, or maybe you want to submit your, you just have to screenshot your figure lah. Okay, which means like this one lah, the figure like this one, like this one. Okay, or maybe you can actually just submit your Excel file, so that will be easier lah. Okay, so this one we're gonna try right now, so we're gonna understand what is actually the question lah. Okay, so for the class activity 2, example on how to plot a drying curve and drying rate curve. Okay, so this one we have sorry, we are using a dryer. Okay, so we put the sample. For example, in your case, you are using the carrot. Okay, in a place where you have a 0.4 and 0.4 cm squared surface area, and then this one is placed in 70 hours of dryer. Okay, and you put in the same constant temperature. So from time to time, you will weight the sample, okay, the tray. And also here also mentioned that the initial moisture content of sample is 89%. So this one, remember that you have tried at the lab, okay, you have done this lab, which means that the percentage of moisture of wet liquid that you get is actually from the moisture analyzer. Okay, so I repeat again, you have this one is actually example of drying process, and you are using a small sample here, 0.4 to 0.4 cm, and you dry for 70 hours at constant drying condition, and you have also have measured the wet basis moisture content, which is 89%. Okay, so by using the moisture analyzer. So the question asks you first, you have to plot the drying curve, and also you have to plot the drying rate curve. Okay, and then you have to estimate the rate of drying at constant period. So which means that you have to identify the constant rate, and then you have to identify the critical moisture content. So which means that the point where the constant rate becomes the falling rate, and then you have to identify the equilibrium moisture content, which means that the point where there's no more water removal, and the free moisture content. So which means that you have to use the formula lah, okay, to actually to calculate the moisture, free moisture content. So we're gonna see step by step how to actually get these things lah. So first, what you're gonna do, this one is actually your raw data lah, okay, and then this one is your initial moisture, initial mass. Okay, this one is your initial mass. So you can see that we are doing the lab for 70 hours, and you weight your product, okay, for each 30 minutes, and the initial product is actually 5 kilogram. Okay, 5 kilogram. Okay, so first what you have to do is you have to calculate the dry solid, because you only know the moisture content of wet basis, but you do not know the moisture, the mass of the solid. So what you have to do is you have to use this formula to calculate the mass of solid. Is actually the total mass minus the moisture content. Okay, so the initial mass is actually 5 kilogram. You minus 5 kilogram multiplied with the 89% of the moisture content, because like you know that from 5 kilogram the moisture content is 89%. So remaining is actually solid. So that's why you will get this answer 0.55 kilogram lah, dry solid. Okay, kilogram dry solid. This is your dry solid. Then you have to calculate the moisture content of dry basis. Okay, so remember the dry basis is the moisture removal divided with the moisture of solid. That's why in the first step we calculate the moisture of the solid. So this one is actually for each time. Okay, so which means that the moisture of removal for that time interval divided with the moisture of the solid. So here X here is actually 5 minus with the mass of solid divided with the mass of solid. So this one is the initial moisture content dry basis at the point 0. Okay, so this one here. Okay, you can see that when you calculate the dry basis, it is 8.09. Okay, that's why you get this answer lah. Okay, so which means this formula is we're going to use to measure the moisture content dry basis for each time. Okay, so this is the formula, the moisture content removal divided with the time. Okay, so that's why you can actually calculate the water removal rate, delta X over delta T, which means that is step 3 here. Okay, step 3 here is actually you have calculate the moisture content, okay, X here for example, and then to calculate the water removal rate, you have to use this formula, Y1 minus Y2 divided with X2 minus X1. Okay, that's why, for example, here in the minute 60, okay, minute 60, you will get 3.86 minus 2.7. Okay, 3.86 minus 2.7. You want to know the removal rate here. So 3.86 minus 2.7 divided with 60 minus 30. Okay, you will get 0.04. Okay, that's why you get this answer lah. Okay, I repeat again. For the step 3, it's actually you want to calculate the water removal rate. Okay, to calculate the water removal rate is by using this formula lah. So which means that the moisture content, for example 60 here, moisture content of 3.86, you minus the 2.7, so you know that how much water be removed in 30 minutes divided with 60 minus 30, you will get 0.04. Okay, so you will do for each of the time lah. Okay, you calculate the moisture content of dry basis for each time, and also you calculate the water removal for each of the time. Okay, so that's how you get this step 3. Okay, so now you're gonna see, you're gonna plot the first you have to plot the drying curve lah. Okay, so for the drying curve, it's actually the moisture content of dry basis versus the time. So you will get this graph. Okay. So we're gonna see the Excel. Okay. So first, you're gonna step 2. Okay, you have know the dry solid. So step 2 here is actually you will actually calculate the moisture content dry basis. So what you do is actually you use the formula to calculate where you know the mass of the product, you minus the amount of solid, you divide it with the solid, so you will get this answer lah. Okay, to make sure that this one is actually the dry solid, to make sure that you put when you, for example here that I don't have it, for example I don't have this one. Okay, okay, you have to make sure that you put this dollar sign. Okay, dollar sign. Okay, because like you want to make sure that every time that it's minus this 0.55, it's actually, it would actually go for 0.55. It do not go to another column lah, or another row. For example, if you don't have this dollar sign, and we drag, it will not capture 0.5 here, it will capture the next row. So to make sure that every time it captures 0.55 here, okay, you have to put the dollar sign here. So every time that another row want to calculate, it will actually refer to the same row. Okay, you can see here, the same row, which is G5 here. Okay, otherwise it will go to G6, G7 according to the row. So to make sure that it will actually only minus this value, you have to put the dollar sign. Okay, that's why you will get the dry basis lah. Okay, and then to calculate the water removal rate here, okay, this the first one definitely there is no water removal, so the you would only have to put 0. Okay, but then for this one, okay, you have to do like this one lah, which means that the answer for it the water here, for example here, 5 minus 3.86 divided with 30 minus 0. Okay, you will get this answer, and then you have to drag lah. Okay, so then you will actually get the same lah. So which means that if I do not have the value here, okay, example here, I just have to drag to the bottom, you will get this answer lah. Okay. Okay, so now you have to go for the step 3. So now what you have to do is you have to plot a drying curve. So this is a drying curve, which means that the value is actually for the y-axis is the moisture content dry basis, and also the time. So you will get this graph. Okay, you can actually plot this graph. So this one is your drying curve. Okay, and then the next question asks you to plot the drying rate curve. Okay, so step 5. Tak apalah. Okay, next step is actually you have to plot this drying rate curve. I think that in my slide, I put step 5 is I plot the water removal versus time. This one is actually just an extra. Okay, but then the question asks you to plot water removal versus moisture content. That's why you go for the step 6, which is the drying rate curve lah. Okay, so this one is the drying rate curve, which means that the drying rate here versus the moisture content of dry basis. This one is your y-axis, this one is your x-axis. Okay, so that's how you get this graph of drying rate curve. So this one is your graph lah. Okay, so then what happened is from this graph you can actually know all these the properties lah, which means that the question asks you first what is actually the moisture content at the constant rate. Okay, so you can see here that we have 2 points here where it is constant, so that's why this one is actually the answer lah. Okay, so okay, you can see here that this one is actually your constant rate, so that's why you go here. Okay, the answer is 0. Okay, the constant rate is at this point. Okay, this one is the initial rate, and then it goes for the constant rate, and then it goes for the falling rate. This one is your falling rate, and this one is the point where it becomes 0 lah. Okay, so this one is the constant rate. So you want to know what is actually the moisture content at the the drying rate removal at constant period. Okay, so that's why you can actually get the answer 0.045 lah from basically from the graph. Okay, you can see that the drying rate at the constant stage is 0.045 kilogram water per minute. So this is the first answer lah. Okay, and then the question also asks you where is actually the critical moisture content. Okay, you can see here that this is actually the moment where it changed from constant rate to the falling rate. So this is your critical moisture content. So critical moisture content, you go to the bottom here, to the x-axis here, you actually found out that the critical moisture content is 4 kilogram water per kilogram dry solid. So this is the answer for your critical moisture content. And then the question also asks you to found when is actually the point where it become zero removal rate, or we call it as a equilibrium moisture content. So the answer is 1.12. This one is actually not obvious from the graph, so that's why you have to go for the table here. The moment that it becomes zero is actually the moment where it's become equilibrium, so that the moisture content of it become equilibrium is 1.12. Okay, so I repeat again, to interpret this drying rate curve, first you have to identify the stage lah. So which means that this one is the initial stage, this one is the constant stage, and this one is the falling stage. Okay, and then you also can actually identify the critical moisture content, which means that the moment where the constant become falling, so this one is your critical moisture content. So you get this value here, which is 4 kilogram. Okay, and then you also can know what is actually the removal rate at constant stage. So you go here, the answer is 0.045 kilogram. And the question also asks you about the equilibrium moisture content. So you have to know that when talking about equilibrium moisture content, is the moment where there is no more water removal. Okay, so that's why you will get the answer 1.12 of the kilogram water per solid lah. So this one is actually your answer for the equilibrium moisture content. Okay, so this is how you can actually get this answer lah. And then you can see from our slide, also the question also asks you to calculate the free water. Okay, so this one is the formula. Okay, so what you do is actually, you know, the initial state, initial moisture content, which is 8.09. So you can see from your graph, your table, 8.09. And okay, you want to know, you want to minus with the equilibrium. So the moment it becomes zero, okay, 8.09, you minus with 1.12, you will actually get the free water, which is 6.97. Because like you have learned this one. This one is actually the water that can be removed from the system lah. So that's why you calculate this one. So any question related to our example? Okay, if you do not have question, we can try. You can try this example. I give you around 10 minutes lah. Okay, make sure that after you try this example, you submit the Excel file to our Putra Blast. Okay, this one. Sorry, I did not share it, but submit it to the Putra Blast lah, our class activity. So try this example for around 10 minutes. So we will continue the lecture after that. Okay. Okay. Can we continue?
Boleh.
Before we continue, I just want to ask, just want to check the attendance. Okay. So can I know that Liang Xuan Chang, are you here in the class today? Liang Xuan Chang. So there's no Liang here, so I assume it's no. And then Nor Hazrina Humaira. Are you here in the class? Okay, no. And the next one is Siti Nuraini binti Zainuddin. Are you here in the class? Okay, no. And then Nur Amelia binti Zafalidin.
Yes, Doctor.
Ya, terima kasih. And then Nur Amira Nazira. Nur Amira Nazira binti Sumiran. Akhirnya, okay. Next we have Aina Sofia. Ada ke Aina Sofia?
Ada, Doctor.
Okay, terima kasih. Next we have Nur Fatiha binti Muhammad Sapri.
Ada, Doctor.
Terima kasih. Then Nur Auni Atira. Nur Auni Atira, ada ke?
Ada.
Terima kasih. Then last one, Ko Zermin.
Yes, Doctor.
Ada eh?
Ada.
Thank you. So now we're going to continue our class. So now you're going to learn about the drawing kinetics. So basically, we have several times you can actually predict the drying time if you know all of these properties lah. Okay, for example here, for drying time prediction for the constant drying rate, you can actually know based on this equation. So if you know all these properties, you can actually know the drying time based on the constant drying rate by this equation. And also you can actually know the drying time of the drying of the falling rate period by using this equation if you know all these characteristic lah. Okay, which means that you know the effective mass diffusivity, the characteristic dimension, half-iness of the slab, for example, because like you have to know, as you have learned in the unsteady state class before with Dr. Chong and Dr. Hanani, different types of shape have different way or different calculation that is actually used to actually measure the heat transfer in the system lah. Okay, so that's why shape also make a difference on the calculation of this constant rate period, also dry on constant rate and falling rate drying period. Okay, this one for cylinder and this one is actually for spherical. So that definitely product will affect the how your drying happen lah. Okay. So now we're going to learn for the second learning outcome, which is the drying model. Okay, so drying kinetics. You're going to learn what's actually the function of having knowing about this drying kinetics or maybe drying model is actually you want to create a equation. Okay, if you know this equation, you do not have to repeat a lot of times of your experiment if you want to do drying at different time. If you have this equation, you put the temperature that you needed to do the drying, you can actually predict how much time is needed for it to reach the percentage that you wanted lah. Okay, so now we're gonna learn how to do it, and for this one there's no class activity, so I think that this one is not very critical, but then you can actually maybe in the future some of you gonna use it for the FYP. Okay, But this one is not just about drying. In the future, I think that some of you will do the, for example, like extraction, anything that can relate to time. Okay, you actually can use this model. Okay, if you create this model, it shows it can actually use for different types of application, unit operation, and every type for any kind of food product. But you have to know that different types of food product have different properties, so it might have different equations. So that's the thing that we're gonna learn today lah. Okay, on how to apply it lah. Okay, first, in order for you to have this drying model, okay, you have to calculate the moisture ratio. Okay, so to in the basic of plotting this or maybe to create to know the equation is actually you have to understand about the moisture ratio. Moisture ratio is moisture content of dry basis at time divided with moisture content at initial lah. Okay, so talking about drying model is actually at different times lah. It's actually related to the time, so that's why at different time of moisture content of dry basis divided with the moisture content of initial. Okay, and it actually can be used to apply for many types of food products. Okay, so this is actually the well-known drying model. Okay, the equation. Okay, this one is actually physician that have create a lot of model equation, and what we do is actually we did not actually do a new equation. We just fitted to the model lah, because like different types of model, it shows you different mechanism on how the process happen lah. So for example, that if you talk about Lewis model, okay, Lewis model here, or maybe the Newton model, it's the mechanism of the try to show you that the process happen at constant process, which means that if you increase the temperature, if you increase the time, for example, drying, the drying rate will be almost the same. Okay, the behavior is constant. So that is actually the Lewis model. Okay, and if you talk about the Page model, usually it's actually the combination of constant rate with falling rate. Okay, so that is actually the mechanism of the trying to show you the mechanism on how the process happens. So this one is actually not just the model to represent drying, but this is the most model used for drying purpose lah. Okay, and for today we're gonna try an example, which means that we're gonna use Lewis. Even though that in drying, it's actually a combination of initial, constant, falling. Okay, but that sometimes it can actually fit this model, so it can actually say that your food is actually representing a linear or constant rate drying. Okay, if it's actually fit the Page model, it's actually combination of rate of the constant and falling rate. So today we're gonna see this example lah, but then different types of food have different behavior, so you have to fit the model so that you can actually know what is actually the model that can represent your food products. Okay, so this is the thin layer drying model. Okay, we have a lot of models here. Newton is actually the Lewis, Page, Henderson, Locke, Tuttle exponential, and Fick's second law. So this one is actually the model that you can actually use to represent drying process. But today we're gonna try this Newton lah, which means that we're gonna try Lewis. Okay, so this one is the Page model. This one is the initial one, not initial one. The moisture ratio is actually this model. Representing Page model is this equation here. Okay, but then if you change to the linear equation, it become like this straight line lah. Okay, which means that y equal to mx plus c. Okay, remember that you have about the linear model, a linear equation is y equal to mx plus c, because you want to plot it in the graph. Okay, that's why this one is y. Okay, the x is ln t, and the slope is the properties lah, the coefficient, which is n. And for the Lewis model, this one is the y ln mr, moisture ratio, at different time, and the slope is negative k, the coefficient plus 1 lah, which is your intercept. Okay, and for the Henderson is ln MRY, and your time is T. Okay, and your X, this is T, and your slope is negative N, and your what you call it, the intercept is ln K lah. So to know what is actually N and K, you need to plot the graph. So we're going to see the example later, so you can actually see how it's actually going to apply this model lah. Okay, so now we're going to see one example. So I also have uploaded this Excel file, so you can actually see I also uploaded the answer, so you don't have to worry. Okay, so now what is actually that we want to do is actually we want to create we want to fit this data to the model, which is Newton here, Lewis. Okay, this is the model. Okay, we want to fit this data to the model. So, for example, that in the future that you want to draw your Hempadu here. Today we have an example of Hempadu. Okay, you want to draw the Hempadu at for example, that 45 degrees C. Okay, but you do not want to repeat this experiment. So what you do is actually you just use the equation. You can actually predict what is actually the time that required for it to reach, for example, like 32%, okay, 55%, or maybe you want to know what is actually the drying time that's needed. Okay, so you do not have to repeat you do not have to repeat the experiment. You just have to use the model, and you can actually know that what is actually the time that you can actually stop the drying process. So that's actually the function of having this model lah. So in order for you to use this model, you have to know that is it your data fitted the Newton model. If it's fitted, you can actually use it for the application of knowing, for example, that for 55 degrees C, for 35 degrees C, for so that you do not have to repeat this experiment lah. Okay, so you have a sample here, Hempadu. Okay, the velocity that you use for air velocity is 1.0 meter per second, and at various temperatures, which is 30, 40, 50, and 60. Okay, the initial moisture content is 80% wet basis, which means that the moisture content inside your food is actually, for example, if you have 100 kilograms, 80 kilograms is actually water. Okay, and the sample here is actually, the weight of sample is 100 here. Okay, like I mentioned, for example, the 100 gram here. So which means that the water is 80 gram, okay, and the solid is 20 gram, okay. And then the question asks you predict the drying time needed for 55 degrees C, which is not here, and the final moisture content of 5% wet basis. Okay, so you want to know what's the drying time required if you do the drying at 55 degrees C, and the moisture content is 5% wet basis. So you want to know that. So how are you going to do that? It's actually you're going to create a model, okay, an equation, so that you can actually you have to fit it with the Newton model, so that you can actually use the equation to predict the time needed for 55 degrees C. So what you do is actually first, the same thing with the first equation, you must know what is actually the dry solid. So that's why 100 minus the moisture content, you get 20 kilogram. I think the answer is gram here. Dry solid. So it is dry solid. And then you have to calculate the moisture content of dry basis. So moisture content of the water removed divided with the minus the moisture solid. To calculate the moisture content of dry basis is actually the moisture content divided with the moisture of the solid lah. Okay. The mass of solid. So the mass, the moisture content of dry basis is the mass of moisture divided with the mass of solid. Okay, that's why the mass of product minus the mass of solid, you get the mass of moisture. Okay, the mass of moisture divided with the mass of solid, you get the moisture content of dry basis. Okay, that's how you can actually open your Excel. Okay, so this is the Excel. Okay, your data is actually here, right? Okay, this one is actually your raw data. Okay, This one is the mass, okay, the moisture content, the mass of your product only, okay, the mass of your sample. So what you do is actually you want to know the mass of the dry basis. So that's why the same thing with the first example where you have to calculate the moisture content of dry basis. So that after you get that, you will plot this one lah, okay, moisture content of dry basis. This is actually your data lah. So you have to plot for 30 degrees C, 40 degrees C, 50 degrees C, and also 60 degrees C. Okay, this is actually your data where you have calculated the moisture content of dry basis. Okay, so then what you have to do? Okay, so then the next step is you have to calculate the moisture ratio. Okay, the moisture ratio is the moisture content at time divided with the moisture content of emission. Okay, so that's why in this Excel here we have the moisture ratio experiment. Okay, this one is experiment. So which means that, for example, here is for this one, 4 divided with 4, because this one is actually your initial moisture content. 4 divided with 4, you will get 1. Okay, and then for the next one here is 3.8 divided with 4, you get 0.95. And for this one, 3.6 divided with 4, you will get 0. And then you go in, and then you go straight lah. Okay, example here that you just have to drag, so you get this answer lah. Okay, so that's how you get the moisture ratio. So which means that the moisture content at what time divided with the moisture content of initial. Okay, you will get the moisture ratio of experimental. Okay, this one is experiment. Then you have to calculate the moisture ratio calculated. This one is for the experimental. Now you have to calculate the moisture content calculated, or sometimes we call it as a theoretical, which means that you're gonna use the Lewis or Newton's equation lah. So this one is actually the Newton's equation. Moisture ratio is exponential of negative k time. So that's how you get the next column here. Okay, moisture ratio calculated is exponential in the power of negative k time. Okay, k time. K you assume it to be 1. Okay, negative k, we put k here equal to 1. Okay, negative k time. Time is here lah. Okay, this one is your time, and then as equal to exponential in the bracket negative k multiplied with time. K here first we assume it to be 1. Okay, just assume to be 1 first lah. Okay, so that's why k equal to 1. So this one equal to exponential in the power of negative k time. And remember to put the dollar sign lah, dollar sign here, because you want to make sure that it always go for the same box. Okay, so then you just have to drag lah. Okay, you just have to drag this one. You will get this data lah. So you assume it to be k equal to 1. So when you plot the data, you can actually see. Okay, this one is for the your experimental, and this one is actually for your theoretical, which means that you calculate based on the Lewis equation. Okay, but in this case, okay, if you want to fit the model, you have to make sure that this line is actually nearer to this line. Okay, that's why we call it as a fitted the model. We want to fit this line here, the Newton's law line here, to this model. How to do it is actually by you have to change the value of k. Okay, to change the value of k, you have to minimize the difference of this data lah, which means that you have to change the square root of difference. Okay, so you want to know that what is actually the difference between experimental and also calculated. Okay, so that's why you have to sum of square here. Okay, you have to calculate the difference between experiment and calculated. Okay, you want to know that so that you can actually change the data, so that you can actually assume the k value, so that you can actually fitted the data lah. Okay, so what you do is actually you calculate the percentage of error lah. So what you do is actually here, okay, uh, you just have to calculate the difference. So which means that, for example, here 1 minus 1 is 0 difference. 0.95 minus, okay, 0.95 minus 0.36, and also for the next one lah. So which means that you have to know what's the difference between experimental and also your calculated or your theoretical lah. So you know the difference first, and then you just have to drag lah to actually know the difference between the experimental and calculated. And then after you know the difference, you calculate how much the difference. Okay, so that's why you have here sum of square of the F9, which means that all of this sum square of F9 until F21, this one. Okay, so this one, okay, you have calculated the difference between experimental and calculated. You will get this data, and then you have to measure this one lah, the amount of the error. So you calculate SSQ, and then you put this data here, sum of square of F9 until F21. You will get this data. Okay, so you have this data lah. Okay, so that's how you calculate the SSQ. Sum of square F9 until F21 is actually the difference between experimental and also calculated. Okay, so this is the formula lah. Okay, so now what you're going to do is actually you're going to use a solver. Okay, okay, how you're going to do it is actually here we have the instruction here. Because you want to change this value of k. If you change this value of k, you will actually get this line here to become nearer to the your experimental data. So for example that if you want to adjust manually also can. If you want to adjust the solver also can. Okay. If you want to use the solver also can. For example that you in the beginning you assume it to be 1, but then if you put it like 0.5 here, you can see that the line started to become nearer to the experimental lah. For example, that if you take like 0.9 or maybe like 0.8, so you gonna manually it's gonna be difficult, but that's why we use the solver lah. Okay, I think this one also being taught by Dr. Chong in the class, Excel class. Okay, in the food engineering class. So what you're gonna do is actually click data. Okay, first you have to click data, and then you have to click solver. Data, you click solver. Okay, then you set the objective, click SSQ box. You click the objective here, okay, to your SSQ, and then you set to minimum because you want to minimize the error so that the graph here will be nearer to your experimental graph. Okay, and then by changing the value of k, and then you solve. Okay, the graph become nearer, it's fitted, and the value of k also changed. So this is actually the value of k for Hempedu lah. Okay, at 30 degrees Celsius. Okay, this only represent for 30 degrees Celsius. Okay, so I repeat again. You have the value of SSQ, which is the combination of the error of between these two lines here. Okay, and then you also have the value. You want to change the value of k lah. So if you minimize the error, you will actually get the value of k for the temperature of 30. For example, in the beginning we just put 1, right? Okay, but then you want to make it the line of experimental and the Lewis line is actually nearer. What you do is actually you want to minimize the error, so you put you use a solver. So you click data, you click solver, you set the objective of the SSQ to minimize the error, so you change the k value, and then you click solve. Okay, and then you found the value of k, And also you found out that the line is actually nearer lah. Okay. And then you have to repeat again the same process for each of the temperature, 30, 40, 50, 60. Okay. And then you do the same thing. You can see here that we have a solver, and then we set soft. We will change lah. Okay. And also here for 50 degrees C, you put the data. Okay. And also for 50 degrees C, solver, you put it. Okay. And then you get the value of K. Okay. So you get the value of K for each temperature. And then you have to create another equation. Okay. So this is your data of K. So to get at 55 degrees C, you have to plot this data lah, because like this one is actually the equation of the Arrhenius equation. So you have to plot ln K over 1 over T. Okay, Y and X plus C. Okay, ln K with the ln K is your Y, and 1 over T is actually your temperature lah, 1 over temperature. So you have to use the Kelvin unit. Okay, so that's why ln K, the value of K that you obtain from each of the Excel. Okay, you ln K8, you have this data, and the temperature is 1 over each temperature. You will get this data, so you plot the graph. Okay, so from this graph, you will actually get the slope and also the intercept lah. Okay, you can see that the slope is negative EA over R, and also the intercept is 1A, so you get the value of each. So you can actually get the EA and also the A. Okay, so this is the K for the, you want to know the K for the 55, because like the function of you plot the graph is you want to know the K for the, you want to know the value of EA, and also you want to know the value of A. Okay, so that you can actually use this formula to get the value of K for 55 degrees C. That's why you use this formula, you get the value of K. You use the equation of K, you can actually get the value of K for the 55 degrees C, which is the question asks you. And then you repeat again to do the same table, which means that you plot for the 45 degrees C, you plot again the moisture moisture ratio calculated by using the Newton's law. Okay, and then you calculate the so you calculate the moisture ratio, and then you calculate again the weight of sample. Okay, weight of sample, and then you calculate again the moisture of the wet basis. Okay. So after that, you can actually know, because the question asks you what is actually the drying time needed for the moisture, drying time needed for the moisture to be 0.05 of wet basis. Okay, this one. So the question asks you at 0.05. Okay, so you have plot this graph, plot this table for the 55 degrees C. So what is actually the time needed for the drying time at 55 degrees C to reach 0.05. So you can see that the value is actually between 0.06 to 0.21 here. Okay, so you do interpolation. You do the interpolation. Okay, do the interpolation, you will get the drying time is 6.05 hours. Okay, or maybe if you have plot the graph, you can actually see that the time needed for it to reach 0.05 is actually 6.05 hours. Okay, so this one is actually just the application of using the model lah, this model. You can actually use it for different types of model. It's okay for this one. This one is actually for those who's gonna use it for the FYP. You can actually use it and like a draft lah, okay, to apply for your application. That's okay. But this is just the idea on how you actually can. So if you do not uh, uh, can come and okay, do you have any question related to the drawing kinetics? Okay, if you do not have any question, can we take a rest for around 10 minutes before we start? Okay. Okay, because like in the last part here is actually will be included in your final exam. And also this one also will be included in your assignment. Okay, this one, even though this one is an example, but then this one I just simply put as assignment so that you can actually send this assignment, this example as an assignment. But the due date will be before tomorrow lah. So I think better that you try this assignment here today. Okay, and then you just submit it because like this one will be 5%. So make sure that you try this as even though that this one is example, but I just put as assignment so that you do not have to do two things lah. Okay, make sure that you try this example. Okay, and then make sure that you submit this assignment example here before tomorrow night lah. Okay, because I will give you until tomorrow. Okay, and you have to make sure that you submit because this one is actually your 5% lah. Okay, I do not want to make another assignment. Just use this one as your assignment, but make sure that you submit before next before like 12 next tomorrow lah. Okay, otherwise I will give you 0 marks. Okay, if you can see that in Putra Belas, I just put if your late assignment is actually 0 marks lah. Okay, remember that this one is actually 5% lah. Okay, we will continue again at 9:40 lah. Thank you. Okay, now we will continue to finish our class. Okay, so please pay attention to this one because this one will be included in your final exam. So this one, we will learn about the effective moisture diffusion. Okay. Okay, so you're gonna learn about the effective moisture diffusion. So basically, we have learned this one in the first week where we have learned about how moisture being diffused during the drying, which means that from high concentration to high concentration of water to the low concentration of water, and also about the definition is actually to quantify the rate of moisture diffused through the solid material. Okay, so which means that if you have like very high value of D, the effective moisture diffusivity, which means that the drying process is actually more effective lah. Okay, so if you have like high D, it means that the rate of the removal of moisture diffused from the solid to the surface is actually high lah. And then this one is actually described as Fick's second law. Okay. And the Fick's second law is stated that about the rate of change of the moisture content to the effective diffusivity, and also the special distribution of moisture, which means that the surface and also the inside of your food lah. Okay. And then this one is the according to the Fick's second law, this one is actually the equation lah, which means that the moisture ratio is actually equal to this equation. And this one can be simplified into this linear equation, the straight line one. Okay, so y here is actually y along mr, and your x here is actually your t, and your slope is this unit. It is in the bracket here, and your y the intercept is this one lah. Okay, so y here, x is your sine. And also this one is your slope lah. So for example here the slope is equal to negative pi squared diffusivity divided over 4L squared. So if you rearrange this equation, you will get this formula lah, which is the effectiveness is actually equal to slope. Okay, the slope that you get from the graph multiplied with 4L squared divided with pi squared. Okay, remember this one, L squared is actually the thickness, but remember that you also have to do this one in the heat transfer, unsafe heat transfer. You have to remember that the L is actually only half. Okay, even though that the thickness is, for example, at 10 cm, so your L is only half. Okay, 5 cm. So this one is actually the common mistake that students make the final exam, where they change, they know that the thickness is 10 cm, for example, and they did not change the L value. L is actually only half. You know that when the drawing happens, it actually from the surface to the center. Okay, it does not involve in the whole thickness. Okay, you assume that every surface is actually bottom or top is actually surface, and then in the middle is actually the deepest point lah. So that's why even though that they give you thickness, the L value is actually half weight, which means that if you give your thickness 10 cm, the L is actually 5 cm lah. So this one is actually the step-by-step of the example that I'm going to show you after this. Okay, so this one, even though this is example, like I mentioned just now, this one is also your assignment. So please make sure that you try this assignment, okay, and then you submit before midnight tomorrow lah. Okay, this one is your 5%. And this one is also be included in your final exam. So please try your best to do this assignment because it's also as an exercise lah for you guys before you go for your final lah. Okay. So first is you have to calculate the moisture ratio. So remember that this one I have taught you guys in the second example, which means that to calculate the moisture ratio is moisture content at different times divided with the moisture content at initial. Okay. And then you have to plot the graph of ln MR versus T lah. So you have to calculate the ln MR versus T, and then you determine the slope. You determine the slope here, and then you calculate this effective lah, okay, the effective moisture diffusion, okay, effective moisture diffusion value, okay, because like the question we ask you like this one lah, so the question ask you to calculate to determine the effectiveness value lah, okay. So this is your assignment. We're gonna do it together, and also I also have, even though that I give you the blank table, I also give you the answer lah. So make sure that even though that I give you the answer, please try this at home lah, and then maybe today right now, okay. After that, you can actually just submit the Excel file. Okay. So this assignment is provided the sample weight at different times, and the moisture content also been given to you guys. Okay, so you don't have to calculate the moisture content. In the final as well, you do not have to calculate the moisture content dry basis lah. I will give you like this kind of tables. Okay, so given to you the sample weight, it given to you the time, and also it be given to you the dry basis. Okay, and then it given to you guys as well the thickness. Okay, 0.9 cm. But remember, okay, this one is the thickness, so the L value is 0.45. Okay, so first you have to calculate the moisture ratio. Okay, because this one is your raw data. Okay, I have already been given to you the moisture content dry basis, so you have to calculate the moisture ratio, which means that moisture content at time was divided with the moisture content at initial. So for example, that this one 9.5 divided by 9.5, you get 1. 8.75 divided with 8.9, you get 0.21 lah. So and then you drag lah. But then for the final exam, you do not have Excel, so you have to calculate one by one lah, the moisture ratio. Okay. After you calculate the moisture ratio, you calculate the load moisture ratio. So you will get this answer. Okay. I repeat again, this one being given to you. And then you have to calculate the moisture ratio because you want to plot log MR. So moisture ratio is the initial at the time, moisture content of time divided with the moisture content of initial. So this one 9.5 divided with 9.5, you got 1. 8.75 divided with 9.5, you got 0.921 lah. And then in the final exam, you have to make sure that you bring your calculator to calculate this moisture ratio lah for all of it, because you do not have Excel file. Okay. And then after you get the moisture ratio, you calculate the loss moisture ratio. This one. After that, you plot the graph of loss moisture ratio versus the time. Okay. And then if you you put you right click and then you put the equation, you will get this straight line here. Okay, so you know that the slope is negative 0.0074. Okay, so repeat again. For the second step, you have to plot the graph, which is log MR versus time. Okay, so in the final exam, I will give you graph paper. You have to plot the graph lah. Okay. So you have to plot the graph, okay, and then you just after you put the point, you draw the straight line lah. Okay. After that, you know that the log MR versus time. So you get this equation. So from this equation, you will get the slope. Okay, which is you get negative 0.074. Okay. You right click, you will get the equation lah, and then you get slope 0.0074. And then you calculate this effective diffusivity. You remember again, I mentioned L is actually half. So make sure that even though the question gave you 9 cm, you have to know that you have to use half of the thickness. It is 0.0045. Okay, you have to remember again another one. You have to convert to SI unit. Okay, given to you to cm, but remember to convert to meter. Okay. And then you put this equation here. Don't worry, I will give you the formula. Okay, so you do not have to memorize the formula. But finally, you will get the final answer. This is your final answer. So you can see as well this Excel file. Okay, I also have uploaded, even though that the I give you the draw, I also give you the answer lah. So you can actually try this one. But this one also I given to you. I also give to you the what you call it, not just because like in your final exam, you're not be able to have this kind of equation, right? So what I'm gonna do is actually I will give you like 2 points. For example, that I said that you have to calculate the slope from 100 to 120. Okay, for example here. Okay. Okay, that's why here is actually we have two form graph and also form calculation. For example, in the final exam, I give you I stated that you have to calculate the slope from minute of 100 to 120, for example. Okay, so you calculate the slope lah. For example, that y2 minus y1, right? And divided with x2 minus x1, you will get the slope. Okay, and then you use that the slope to actually calculate your you have to do the calculation lah. Okay. So this one is the final answer. Okay. So this is the book that I use for our class. So if you have any question or you want to refer to the books, you can actually refer to the books lah. Okay. So do you have any question related to this example here? No question. So, but remember, make sure that you submit this one because this one is 5%. So I assume if in the Sunday morning I did not see any submission, I just put 0 marks lah. Okay. But also I also have mentioned in the Putra Blast, if the late submission, I assume it to be 0 lah. Okay. And then I'll make sure that you study this one, and this one is actually the final example is also in your final exam. Make sure that you study this one, and maybe you can actually try it in the graph paper, okay? Because that you're gonna plot the graph, and also you're gonna find the slope based on the data that I've given to you guys. Make sure that you know how to calculate MR, load MR, okay? And then I think that if you do not have any question, I think that's all for today. Okay, we're gonna see each other in the final exam. Do you have any questions? So okay, there's no question. So and if you have, but then remember, you just have to focus on that part lah. Okay, you make sure that you do not you use half of the error. Okay, because sometimes you don't always make like correction on that, make mistakes on that lah. Okay, so I think that's all for today. So all the best for your final. Do your best. Please submit your assignment. Okay, that one is 5%. So I wish you all the best for your final exam. So we're going to see each other in final exam lah. So that's all for today. Thank you everyone.
Thank you,